morning, good afternoon, good evening. Welcome to Bonsai and NVIDIA joint webinar. Today's webinar is Building Industrial Strength AI Models for the Enterprise. This webinar will be recorded and available for replay after, and the slides will also be available to view. And I'm glad to have Jim McHugh, the VP and GM of NVIDIA, and Mark, the CEO of Bonsai, to join us for this webinar. With that, Jim.
All right, thank you so much, Renee. So yeah, I think it's going to be a great session today. We have a lot of very interesting information to share with you. And let's just jump right into the first slide. I want to actually give you some context of why this is possible. You know, for the last 30 or maybe 40 years or so, we have benefited from one of the most powerful technological revolutions that anyone has ever seen. And traditionally, we refer to this as Moore's Law, which was an architectural innovation that makes microprocessors better and better, more and more performant. And the goal was to find instructional level parallelism, because as many of us probably know to some degree, a program is really just a sequential list of instructions performed one at a time. But some really smart computer scientists figured out how to do some of these in parallel. And this entire process was also supported by another law called Dennard scaling, which basically said that we can add more and more transistors and we can run them faster and faster at a lower and lower voltage. This allows us to continue the advanced performance within the same constant power envelope. And in the course of the last 30 years, the microprocessor improved by nearly 1 million times. But unfortunately, as all good things start coming to an end sooner or later, it was in the last several years it started to slow. The ability to harvest this parallelism out of sequential instructions started to diminish. The number of transistors that needed to be added in order to squeeze out even a tiny bit of extra performance was simply too costly because it ran up against the semiconductor laws of physics. And there was only so far we could push this before Dennard scaling started to fail on us. And that is what the blue line is basically showing. The ability to harvest parallelism out of the sequential instructions and the productive architectural innovations that were needed started plateauing processor performance. So what used to grow at 50% a year, compounded improvement, is now improving only at about 10%. But that said, the other line shows something that is really interesting, is that transistors are abundant. And basically, that observation was the reason why accelerated computing was created and why it works. And this is why the reason NVIDIA created the concept of GPU computing. So if we go into the next slide, I'll explain a little bit about that. So GPU computing actually works because NVIDIA recognized that the microprocessor is incredibly good at sequential instructions. So NVIDIA also realized that there are certain important applications that include parallel computing aspects that if we could figure out how to offload these parallel processes from the microprocessor that was really good at sequential processing, we could provide incredible and game-changing speed up. And NVIDIA brought this incredible speed up to general compute in 2008 when we created an architecture called CUDA. It does what generally available computing cannot do because we worked at the architectural level, the system software level, the algorithm level, and we work at the application level as well. If you look at the green line, that is basically the line that NVIDIA is tracking to. And some people describe that progress as Moore's Law squared. Because if you look at it, you're getting an incredible speed up. It's a big speed up over the natural microprocessing performance, and it appears to be moving faster than the rate of transistors themselves. And that's only because we thought of the entire stack. So with this new computing model, we've seen great advances in virtual reality, fluid dynamics, molecular dynamics, and today what we're going to be talking to you about the great advances we're seeing in artificial intelligence, deep learning, machine learning. So we've seen this play out in many different industries. If you go to the next slide, I'll lay out. It is true that NVIDIA is famous for the world of gaming. And then as I described, we took that into the world of virtual reality. So we help people create the realities and see things in different ways. And through serendipity or destiny, it was also discovered that this actually worked really well in the world of artificial intelligence. And Alex Krizhevsky helped the world understand that when he developed AlexNet. And now, as we move into self-driving cars, healthcare, so many different avenues where deep learning and AI can play, the ability to take advantage of this technology is just really astounding. And so with that, I'd like to hand over to Mark at Bonsai, because I think he can share with some great ways that people listening today can take advantage of these technologies to do some pretty amazing superhuman things.
Great, thank you for that. So what I want to talk about is what we mean when we talk about AI, and what kinds of problems can we apply this to when we look at our commercial and industrial enterprises. AI really builds a very broad spectrum of capabilities that people are looking to employ to add intelligence to their applications, whether that be a software application or a hardware application. And that runs the gamut. It runs everything from complete autonomous systems to pure data mining scenarios. So there are situations where you have collected a tremendous amount of data from Internet of Things sensors, from customer interactions, from your equipment itself. And what you really want to do is to be able to dig into that collection of data and ferret out the insights and the intelligent nuggets that you can use to help drive your business and make reasonable predictions about what to do moving forward. That's one extreme. On the other end of the spectrum, you have situations where you have systems that interact with the real physical world in some meaningful way. So this is not just collecting data, it's not making decisions about which movies you want to watch, where the act of someone following up on that prediction or not following up on that prediction will have a material impact to their enjoyment of the movie, but it will not affect a piece of operating equipment in a factory, for example. When you get to that end of the spectrum, the kinds of concerns you have are different. And this tends to be the realm that we classify as industrial AI. These are things like advanced robotics, building intelligent factories, and so on. And when you look at these problem spaces, there are a few things that make them really interesting and really unique. To start with, the problem space itself is very dynamic. When you interact with one of these systems, how it's going to behave is not necessarily always predictable. If we look at a self-driving car as an example, if you have a car and it drives up to an intersection, and it has been at this intersection before, and it has seen the array of cars sitting at that intersection that it has seen in previous encounters, it nonetheless, regardless of the decision it makes about what the appropriate way to steer the car through the intersection is, and not presume that the other cars, even though they're present in the same way, will behave the way they did before. It is a very dynamic environment. It has very few constraints placed on it, only the rules of the road and people's decisions to adhere to them. And so you have to be able to build intelligent systems which are able to deal with that kind of environment correctly. When you look at environments like this, being able to leverage domain and subject matter expertise becomes critical. It's not enough to just say, we're going to let the machine learning algorithms figure it all out on their own. You actually want to be able to help the systems learn more quickly, to guide the instruction. It's interesting, in machine learning, there's another side of that coin, and that other side is machine teaching. And teaching doesn't get a lot of attention paid to it, but it's just as important. No matter how good the learning algorithms get, you always will have to teach these systems. In many cases, teaching these systems is presented in the form of very large data sets that have been crafted appropriately. But in many situations, you want to present that teaching in the context of the subject matter expertise that you already have. I will often say, just as an intuitive approach here, humanity learned calculus over many millennia, and we can now get most high school and college students through a calculus course with fairly readily, and that's primarily because we have a curriculum that we can follow. We understand the core concepts that they need to acquire. We have good lesson plans for teaching it to them and helping hold their hands and actually doing the teaching process regardless of how the underlying mechanics of the learning in their brain are happening. Machine learning and machine teaching are no different. And in this case, the subject matter expertise that matters is the expertise, that core strategic asset that is already within all of our organizations. Being able to bring that to bear is critical, and it allows you to do a bunch of interesting things. One of the most important is explain what's going on in the system. We don't want machine learning to be a giant black box. We want, when the system takes an action or makes a prediction, to be able to understand why and to be able to not only explain it, but be able to iteratively improve upon our models and our designs as we understand why it believes whatever it was doing was the right thing to do. So in this case, being able to do that teaching in these industrial contexts is very important, and oftentimes we'll leverage simulations quite heavily. So this is where we're quite happy to be working with NVIDIA. Not only can they bring the extensive compute capability to bear, which is very necessary for the modern types of machine learning algorithms that we're using, but simulations similarly can leverage that. So the combination of both of these is what really allows us to build these rich teaching environments so that we can add intelligence to these algorithms. When we look at the kinds of systems that people are actually building, real-life, real-world use cases, it's fun to talk about the advances we can make in the state-of-the-art for playing various intellectual games, Go, chess, poker, etc. It's another thing when we start to talk about what are we actually applying these systems to, what are the real-world problems that we see. So these include industrial robotics, as you would expect, but it extends beyond that. You can look at things for fleet operations, intelligent supply chain management, making better control for your heating and ventilation and air conditioning systems, adding that intelligence into your appliances more generally, making smart factories, dark factories, enabling these kinds of capabilities, and generally improving operations, adding intelligence to your operations, and adding intelligence to your systems. In all of these cases, leveraging simulations and that subject matter expertise is something that is quite critical. And so this is where Bonsai has attempted to come in and really provide the thing that fills the gap so that you can take machine teaching and machine learning technology and marry the human intelligence with the machine intelligence to build these kinds of solutions. Bonsai itself has been around since 2014, and bringing these things together, really focusing on that abstraction around machine teaching is what has driven this business. The core insight behind this is that no matter how smart you make those machine learning algorithms, you will always have to teach them something. They can be as smart or better than humans, and that will not change. And by building upon that abstraction, we are able to take the low-level mechanics of how the machine learning and the computing happen and, by and for the large part, automate a lot of that with technology so that the developers, the subject matter experts, the chemical engineers, the mechanical engineers who are in these organizations tackling these real-world problems can take their subject matter expertise and talk about how it is that we teach that to the system, what the core concepts are that we need the system to understand, how we can phase a plan of lessons to introduce that, and thus realize solutions to these problems. We do that by providing you with a platform that is very much akin to a database in terms of how it can be thought. With databases, there was a time where they were so common, before they were so common that everyone took them for granted like we do today, where you had to worry about, similarly had to worry about the low-level mechanics of how all that data management took place. Databases solved that problem for us quite nicely, and they did it by giving us an abstraction upon which we can all build. That was the abstraction around the relationship model and giving you a language like SQL with which to express it. So you could now, instead of expressing what the trees that I wanted to use to store the data were and how I rebalanced them and when I would do it and how I span multiple disks, you instead focused on what is the structure of the data I care about and what kinds of business questions do I need to be able to ask of that data. And then I'm going to use the piece of technology, the database itself, to manage the low-level mechanics of how all that happens. What I care about is the result that comes out the other end. Bonsai does the same thing with our platform. We just do it for artificial intelligence, and we build upon that abstraction of machine teaching. So we have built a new special-purpose programming language called Inkling, which is specifically designed to allow you to express what it is you want to teach and how you teach it. It is still a formal programming language and a formal programming system, but it is focused on those abstractions, what it is to teach and how to teach it. We give you the tools that you need to build the solutions in that way. So it is a full development environment stack, and the runtime environment and platform that goes along with that. So you get a command line interface, you get a web interface for management. I will show you the integrated developer environment in a moment. And you are able to use those tools to interface with existing models you might have, to connect to a variety of training sources, going beyond just data to also include procedurally generated data, interactive simulations, etc., and to describe in a declarative way what it is you want to teach and how you're going to teach it. That information is given to our AI engine, which then uses it to construct for you appropriate machine learning models. For a lot of these systems in the industrial AI realm, that becomes deep reinforcement learning systems. So understanding how to lay those out and whatnot is something that our system manages for you based on what you're trying to accomplish. We're able to infer from the code about what you're trying to teach and how to teach it, what appropriate techniques are to use. And so we will automate all of those pieces for you so that it can conduct the training in an automated way. And then when you go to use it, you use it in the same way that you would have used a database, right? So with a database, you take your existing business logic, whether that be in whatever programming language it happens to be in, and you use connectors into the database so that you can interact with it to insert records, retrieve records, perform queries. With Bonsai system, it is the same thing. So you take your existing application code, be it in C++, Java, Python, C#, Ruby, whatever it happens to be, and you're going to interface with the Bonsai platform, the runtime environment, using appropriate SDKs or appropriate APIs directly, and you treat it as a streaming analytics system. So you give it the real-time feed of data that's going through the system, and you get back either synchronous predictions or notifications of important events that can drive certain behaviors within your application. All of this is built on the foundation of GPU computing and computing that happens either on-prem or in a cloud environment. Because we leverage simulation as a primary training source, a lot of customers that work with Bonsai are running in on-prem deployments because they want the deployment of the runtime environment to actually be situated very close to the simulation environments themselves. For other customers, they want to utilize the power and scalability that you get from a cloud-hosted environment. And so we enable you to operate in either mode, in all cases powered by powerful GPU computing from NVIDIA. As you build these systems out, you get a bunch of benefits as a result. So you're able to use your existing development team. This is not about having to go and become a machine learning expert. This is about being able to take your engineers, whether they be chemical engineers, mechanical engineers, or other subject matter experts, and your programmers that you have on staff, and use their subject matter expertise, their knowledge, to solve these real-world problems that you're going after. You don't have to become a machine learning expert. You do have to be able to teach the intelligent behavior that you are after. It also, because you are now able to describe things in terms of these concepts that you wanted the system to understand, whenever it makes a prediction, it is now fully explainable within that context. So you are able to, as an example, going back to the self-driving car situation, if the car were to make the decision that turning left at the intersection in a certain way was the correct action to take, it would no longer be a black box that that was what happened. It would be able to explain to you, in the context of everything that you taught it about driving behavior, about interpreting the sensory input in it that it has perceived, you would be able to explain that decision within the context of those concepts that you have taught, and that enables you to not only gain confidence in the predictions that are being made, it also enables you to iteratively build upon your models. Instead of, if the decision was something that was incorrect, instead of trying to figure out how you tweak the low-level mechanics of the machine learning model and the algorithms that underlie that, you instead focus on, oh, this was an edge case I hadn't accounted for. I really need to go add another lesson to my plan, my curriculum for teaching that. Or there is another concept that I didn't take into account that you really need to understand and learn, and so you can teach that. And then the last one is that you're really able to build these models independent of the other underlying algorithms. You don't have to be dependent on whatever today's latest and greatest implementation is. The pace of innovation on the algorithmic side is very, very fast at this point in time. And so every 6 months or so, the best way to be implementing anything has changed completely. And that means that there's a lot of churn if you are working directly at that level of the stack and building out solutions for the problems that you're facing. You don't want to have to go change your DQN implementation to a DDPG implementation and deal with all the facets that coincide with that. You want to have more intelligent behavior for your machining environment. You just want it to behave better and perform faster. And so in the same way that as with databases, where an improvement in the underlying technology comes as a benefit to your code without you changing anything. You didn't rewrite your SQL queries, they just run faster. As the underlying AI and machine learning technology improve, when you write at this with this abstraction of machine teaching, you focus instead on that and not the low level. The burden of keeping up with those models shifts to Bonsai and the maintainers of these kinds of platforms, such that you recompile your code. You don't change it. You just recompile it. You run the training again. You get the benefits of all of the new algorithms. So these are the kinds of benefits that you can get. And it's really best to see this by just diving into a quick demonstration of the underlying technology. So what I want to show you to set this up is some work that we did together with Siemens. And with Siemens, what we were looking at was how do we enable machines to interact side by side and in conjunction with humans in a more effective way. So what you see modeled here is a Baxter robot. This is a commercial robot that can be obtained quite readily. And this robot is being tasked with the objective of learning to carry a table in conjunction with the human. So it's not that you want the human to follow the robot. It's the other way around. You want the robot to learn how to follow the human's lead. That's actually a very difficult problem in computer science. And so what you see modeled here is you see a robot as it's just beginning to learn. It's just beginning to be trained on this task in the simulation. But what is not directly visible is that there is a simulated human standing on the other side of the table. And that human is exerting forces to lift the table alongside the robot, and the robot is trying to figure out how to work with that. And so what we see is that when you're first starting to learn, the robot really doesn't know what it's doing. Right? The human is lifting the table and exerting forces. The robot doesn't know what to do. Eventually it figures out that, hey, I ought to try to pick this table up, but doesn't really know what's going on. And what you want to get to after training is a system that looks like this, wherein the robot has not only learned to lift the table, it's learned to keep it level, and it can do this while following the unpredictable and dynamic motions of the simulated human on the other side. Once you have the system trained to this point in a simulation environment, then it is appropriate to start continuing the training, but doing that in an environment with real physical humans, or in the case of a lot of industrial applications, with the real equipment or in the real environments. But by getting it to this stage in a simulation environment, you don't have to spend time with that real equipment worrying about the system making a catastrophic decision about what to do. It's gotten a large part of the way there, and you're really tuning and refining what's going on. So what does this look like in the context of the code that you would write? Well, this is a tool called Mastermind, which is Bonsai's integrated developer environment. And let me load up the code that corresponds to the simulation that you were, the training that you were just looking at. So what we see here is we see Inkling code in the left-hand pane. It will look like a cross between SQL and Python, which is by design. And in the right-hand pane, what you are seeing is a visual representation of the concepts that we are trying to teach using this code to the robot system. It's a very simple model. So we are teaching it 3 basic concepts: how it needs to lift in tandem with the human, how it needs to keep the table level by balancing the torque that's applied to the table. If you have 2 arms and you're not applying forces exactly evenly, of course, the table will start to tip. And then, having learned those 2 concepts, how do we integrate them effectively to follow the lead of the human in achieving the objective we've set out? So, when we look at the code, this is a streaming analytics system at the end of the day. And so you have a bunch of schema that are modeling the kinds of data that will flow through the system. There's the state, which is representing the state of the environment itself. In this case, this is modeling the robotic armatures and the various joints on them. The kind of commands that can be taken, these are the actions that you can take on using the robot to affect the state of the environment. And a configuration for the simulation environment itself, which becomes very important as we set out the lesson plan for how we're going to train this system. We're going to connect to a simulation environment. In this case, we're using Gazebo, which is an open source simulation environment for robotic systems with a physics engine entailed. You can integrate with a variety of simulation environments, however. You can do, if you're working with an HVAC system, for example, you could work with Energy Plus. Or if you're working with a mechanical system, a mechanical engineering type model, you might use MATLAB and Simulink. Any of these simulation environments are germane and can be brought to bear, including ones that you can author yourselves if you have custom simulations for your work. You would just buy those using the appropriate SDKs into the platform, and then you're able to expose it to your Inkling models to describe how it's taught, regardless of the fact that the simulations might be implemented in C++ or Python or some other lower level language. Having talked about the schemas and the simulator that you're going to use, the next piece are the concepts. So the concepts that the system is going to be teaching are declared. And so in this case, if we're talking about tandem lift, it's an estimation style concept. We're trying to learn to estimate the amount of torque we should apply to any motor in the armature so as to appropriately lift that table in tandem with the human standing on the other side. We're going to predict that command, and we're going to do so by looking at the input that's coming directly, the state of the environment input that's coming directly out of the simulation itself. You can have subsequent downstream concepts, like the follow human lead one we see here, which is following those higher order concepts, the ones which were directly following the input, so that you can learn more and more and more complex and nuanced behaviors, or you can learn to recognize, when it's not a skill, when it's a perception task, you can learn to recognize more and more complex objects or things that have been built up from more primitive concepts. Having done that, for any one of these concepts, we still have to talk about how we teach it. So that's where the curriculum comes in. Here, if we're looking at lifting this table in tandem, we want to train that concept that we talked about. We're going to use the simulation environment that we described earlier, and we're going to pursue a certain objective. So you describe what success looks like. You don't describe how to literally calculate the motor torques that will achieve the good objective. That's what the system is going to learn. But what you do need to describe is what a good result looks like. And so that's what we do here with the objective. In this case, the objective, the reward that you get for lifting and having doing so in tandem with the human, is described in the simulation context of the simulation environment itself. And so then we would need to describe the lessons that we're going to follow. And this is where we progressively build things up. And here it's useful to make an intuitive appeal just very briefly, and then looking at how that corresponds to this code. I have a young son. He's 4.5, and he's learning how to play baseball. And when I want to teach him the skill of hitting the ball, I do not start by taking him out to the backyard and throwing fastballs at him. That's where he'll ultimately get to when we're playing the game in real life. But to start out with, it's silly. You wouldn't do that to a 4.5-year-old. What you do instead is you set a ball on a tee, a wiffle ball, and you let him practice with that. And then you set the tee to pop the ball in the air once he gets decent at it. And once he gets good at that, you start to pitch underhand at close range. It's a progression. It's not the real end problem you're looking to solve, but it is a way of phasing in acquisition and mastery of the skill that you are trying to teach. And so that is what we're trying to do here as we describe this curriculum for lifting the table. What we're doing is we start out with a very constrained low range of forces being applied on the other side of the table. So we've configured the simulation environment as part of this lesson to constrain the torque so that there's none. The table is starting out standing on the floor, and the amount of force that's being applied on the other side of the table is constrained to a very tight range. Now, as that gets mastered, we can proceed to subsequent lessons where we start to increase that range. And you can increase it more and more and more as we go through this code so that you can attain mastery over that higher skill level. This results in increased training efficiency. while you don't have to do this, and you could certainly provide a single lesson curriculum to teach it, what you will find is that it runs many, many times faster when you do. And it becomes more predictable, and it's easier for your subject matter experts to guide the instruction. It's a much more natural way to think about how you impart expertise and intelligence is by how do you teach something effectively. So we do that, and we do that for various concepts. So when we talk about keeping the table level, we are now going to match gravity with the tandem force, and we're just going to exert torques in a tight range along the same line. And when we get to, we relax that more and more over time, and then when we learn to follow the human, we are going to keep the table starting on the floor, but now we're going to have the range of forces that are being applied both for lifting and for torque, following a wider range of forces, while also being simultaneously varied. By breaking the problem up into this way, we are enabling the system that's learning to explore and to master things in a much more efficient, natural way, and you get the results that we saw before in the video, wherein the robotic system has learned to carry out these tasks and can now explain to you whenever it's taking a certain action that, in fact, I was doing this because I believed that the human on the other side of the table was starting to unbalance it in this way, and I was counteracting that. And that was more important than trying to lift at the moment because we needed to regain balance so the table didn't topple over. Being able to do that is very powerful. This is a very simple model, but as you build up more complex models for automating manufacturing equipment, for working with your supply chain and understanding the logistics that go inside with that, it becomes much more powerful as you add more and more richness and depth to the concepts that you're teaching, and being able to focus at that level as opposed to the level of the mechanics of how the learning takes place enables you to do a lot of things more quickly and more easily with your existing team and towards the problems that you are looking to solve. That's a quick tour through Bonsai and through how we think about applying machine teaching to these problems and leveraging the immense computing power and capability that we can bring to bear in order to add intelligent behavior to these systems. And so with that, I want to thank everyone for participating in the webinar. I want to thank NVIDIA for co-hosting with us, and I would encourage everyone to visit our respective websites, as you see here, at nvidia.com/AI and at bons.ai to learn more about NVIDIA's work with AI and about Bonsai's platform. And again, thank you everyone for your time and for joining.